A collision is an event in which two or more bodies exert forces on each other for a relatively short time. Although the most common colloquial use of the word collision refers to incidents in which two or more objects collide, the scientific use of the word collision implies nothing about the magnitude of the forces. Some examples of physical interactions that scientists would consider collisions. An insect touches its antenna to the leaf of a plant. The antenna is said to collide with leaf. A cat walks delicately through the grass. Each contact that its paws make with the ground is a collision. Each brush of its fur against a blade of grass is a collision. Some colloquial uses of the word collision are: automobile collision, two cars colliding with each other; mid-air collision, two planes colliding with each other; ship collision, two ships colliding with each other. Overview: collision is short-duration interaction between two bodies or more than two bodies, simultaneously causing change in motion of bodies involved due to internal forces acted between them during this. Collisions involve forces. The magnitude of the velocity difference at impact is called the closing speed. All collisions conserve momentum. What distinguishes different types of collisions is whether they also conserve kinetic energy. Line of impact. It is the line which is common normal for surfaces are closest or in contact during impact. This is the line along which internal force of collision acts during impact, and Newton's coefficient of restitution is defined only along this line. Specifically, collisions can either be elastic, meaning they conserve both momentum and kinetic energy, or inelastic, meaning they conserve momentum but not kinetic energy. An inelastic collision is sometimes also called a plastic collision. A perfectly inelastic collision is a limiting case of inelastic collision in which the two bodies stick together after impact. The degree to which a collision is elastic or inelastic is quantified by the coefficient of restitution, a value that generally ranges between 0 and 1. A perfectly elastic collision has a coefficient of restitution of 1. A perfectly inelastic collision has a coefficient of restitution of 0. Types of collisions. There are two types of collisions between two bodies: one, head-on collisions or one-dimensional collisions, where the velocity of each body just before impact is along the line of impact; and two, non-head-on collisions, oblique collisions or two-dimensional collisions, where the velocity of each body just before impact is not along the line of impact. According to the coefficient of restitution, there are two special cases of any collision as written below. A perfectly elastic collision is defined as one in which there is no loss of kinetic energy in the collision. In reality, any macroscopic collision between objects will convert some kinetic energy to internal energy and other forms of energy, so no large-scale impacts are perfectly elastic. However, some problems are sufficiently close to perfectly elastic that they can be approximated as such. In this case, the coefficient of restitution equals 1. An inelastic collision is one in which part of the kinetic energy is changed to some other form of energy in the collision. Momentum is conserved in inelastic collisions, but one cannot track the kinetic energy through the collision since some of it is converted to other forms of energy. In this case, coefficient of restitution does not equal 1. In any type of collision there is a phase when for a moment colliding bodies have the same velocity along the line of impact. Then the kinetic energy of bodies reduces to its minimum during this phase and may be called a maximum deformation phase, for which momentarily the coefficient of restitution becomes 1. Collisions in ideal gases approach perfectly elastic collisions, as do scattering interactions of subatomic particles which are deflected by the electromagnetic force. Some large-scale interactions like the slingshot-type gravitational interactions between satellites and planets are perfectly elastic. Collisions between hard spheres may be nearly elastic, so it is useful to calculate the limiting case of an elastic collision. The assumption of conservation of momentum as well as the conservation of kinetic energy makes possible the calculation of the final velocities in two-body collisions. Elision. In maritime law, it is occasionally desirable to distinguish between the situation of a vessel striking a moving object, and that of it striking a stationary object. The word elision is then used to mean the striking of a stationary object, while collision is used to mean the striking of a moving object. Analytical versus numerical approaches towards resolving collisions. Relatively few problems involving collisions can be solved analytically, the remainder require numerical methods. An important problem in simulating collisions is determining whether two objects have in fact collided. This problem is called collision detection. Examples of collisions that can be solved analytically. Billiards collisions play an important role in cue sports. Because the collisions between billiard balls are nearly elastic, and the balls roll on a surface that produces low rolling friction, their behavior is often used to illustrate Newton's laws of motion. After a zero-friction collision of a moving ball with a stationary one of equal mass, the angle between the directions of the two balls is 90 degrees. This is an important fact that professional billiards players take into account, although it assumes the ball is moving frictionlessly across the table rather than rolling with friction. Consider an elastic collision in two dimensions of any two masses m1 and m2, with respective initial velocities u1 and u2 where u2 equals 0, and final velocities v1 and v2. Conservation of momentum gives m1 u1 equals m1 v1 plus m2 v2. Conservation of energy for an elastic collision gives m1 u1 2 equals m1 v1 2 plus m2 v2 2. Now consider the case m1 equals m2. We obtain u1 equals v1 plus v2 and u1 2 equals v1 2 plus v2 2. Taking the dot products of each side of the former equation with itself, u1 2 equals u1 equals v1 2 plus v2 2 plus 2 v1 v2. Comparing this with the latter equation gives v1 v2 equals 0, so they are perpendicular unless v1 is the zero vector. Perfectly inelastic collision. In a perfectly inelastic collision, i.e., a zero coefficient of restitution, the colliding particles stick together. It is necessary to consider conservation of momentum, where v is the final velocity, which is hence given by the reduction of total kinetic energy is equal to the total kinetic energy before the collision in a center of momentum frame, with respect to the system of two particles, because in such a frame the kinetic energy after the collision is zero. In this frame most of the kinetic energy before the collision is that of the particle with the smaller mass. In another frame, in addition to the reduction of kinetic energy, there may be a transfer of kinetic energy from one particle to the other. The fact that this depends on the frame shows how relative this is. With time reversed, we have the situation of two objects pushed away from each other, e.g., shooting a projectile, or a rocket applying thrust. Examples of collisions analyzed numerically. Animal locomotion. Collisions of an animal's foot or paw with the underlying substrate are generally termed ground reaction forces. These collisions are inelastic, as kinetic energy is not conserved. An important research topic in prosthetics is quantifying the forces generated during the foot-ground collisions associated with both disabled and non-disabled gait. This quantification typically requires subjects to walk across a force platform as well as detailed kinematic and dynamic analysis. Collisions used as an experimental tool. Collisions can be used as an experimental technique to study material properties of objects and other physical phenomena. Space exploration. An object may deliberately be made to crash land on another celestial body, to do measurements and send them to Earth before being destroyed, or to allow instruments elsewhere to observe the effect. CEG, during Apollo 13, Apollo 14, Apollo 15, Apollo 16 and Apollo 17. The SIVB was crashed into the Moon in order to perform seismic measurement used for characterizing the lunar core. Deep Impact Smart 1 European Space Agency Satellite Moon Impact Probe ISRO probe. Mathematical description of molecular collisions. Let the linear, angular and internal momenta of a molecule be given by the set of R variables pi. The state of a molecule may then be described by the range delta y equals delta p1 delta p2 delta p3 delta pr. There are many such ranges corresponding to different states. A specific state may be denoted by the index I. Two molecules undergoing a collision can thus be denoted by it. Is convenient to suppose that two molecules exert a negligible effect on each other, unless their center of gravities approach within a critical distance b. A collision therefore begins when the respective centers of gravity arrive at this critical distance, and is completed when they again reach this critical distance on their way apart. Under this model, a collision is completely described by the matrix, which refers to the constellation before the collision, and the constellation after the collision. This notation is convenient in proving Boltzmann's H-theorem of statistical mechanics. Attack by means of a deliberate collision. Types of attack by means of a deliberate collision include striking with the body, unarmed striking, punching, kicking, striking with a weapon, such as a sword, club or axe, ramming with an object or vehicle, e.g., a car deliberately crashing into a building to break into it, a battering ram, medieval weapon used for breaking down large doors. Also a modern version is used by police forces during raids. An attacking collision with a distant object can be achieved by throwing or launching a projectile.